So the wind speed of V and the rotational rate of omega. And neglecting viscous effects, write the relationship in dimensionless form. This is the first part of the question. Second part of the question says that we have to calculate the power developed by the prototype wind turbine. So prototype means that the real one. Okay, we have to find the power of the real wind turbine, which has a diameter of 50 meters. This one is the real one, and the wind speed of 8 meters per second. And to understand the power of the real one, we need a model one. Okay, and the model has a diameter of 90 centimeters and the rotational rate of 1200 RPMs and the power output of 280 watts at a wind speed of 12 meters per second. For dynamic similarity, determine the rotation rate and power output of the prototype. Okay, so let me show you. We have a wind turbine. This is the model one. This model wind turbine so this one is the model one. Let me show you. This is the model wind turbine. And the values that are given for it are the diameters. So if you think this one as a circular way, okay, and it has a diameter of, that is, where is the diameter? 90 centimeters. And the rotation rate of omega is 1200 RPMs. And you have the generator here. That generator gives you the power output of, so that work done of 280 watts. And there is a wind over that wind turbine. The wind speed for that wind turbine is that is 12 meters per second. So U infinity is 12 meters per second. Okay. If you remember, I've said that the infinity says that, the infinity subscript here says that we are far away from the object, that its effects are not felt. Here, the wind speed, and then we show it as the infinity. This one is the model one, but for real one, it should be much larger, but I will try to show it as large as possible. So this one will be the real one. Okay. And you will also have the blade here, and you will also have the blade here. Okay. This one will be the real one. For the real one, it says that the diameter is 50 meters. It should go in a circle. Okay. And it has a diameter of 50 meters. Okay. And then wind speed here is 8 meters per second. The U infinity is 8 meters per second. And U infinity I will put at P means prototype, and the diameter P means prototype, and the V dot P means prototype, and this one omega P means prototype, and the diameter, sorry, this one's model. This one is model, and this one is model. U infinity model, and the diameter model is named 9 centimeters. And this is the question, and it says that they are similar. Okay, the dynamic similarity means that the forces acting on this one are proportional to forces acting on this one. Or if you want to get the similarity, you should use the Buckingham's pi theorem, and then air density says that it's same for both of it. So rho model is 1.2 kilograms per meters cube, and the rho prototype is again 1.2 kilograms per meters cube. Okay. These are the values that are given. Okay, but the question says that find the rotation rate of prototype. So prototype means that the real one. This one is unknown, and the work dot power of the prototype, which is unknown. These values should be determined from the model values. Okay, from the model values you have to determine it. Okay, so these are similar. So if these are similar, okay, then we can use the Buckingham's pi theorem, And by using the Buckingham's pi theorem, we can find the similarity ratios. Okay? And then from that similarity ratios, as well as the dimensionless variables, we can find the power of the prototype or real one and the omega of the real one. Now let's do it. So I will go back to the first part of the question, which is A, and then come back again to question part B. Okay, so the Buckingham's pi theorem. So what we have here is that it says that the wind turbine power, V dot, is function of blade diameter, density of air, wind speed, and rotational rate. So that wind turbine power is function of, that is the diameter, the air density, and the wind speed, and then omega, which is the rotational rate. So it says that neglect viscous effects. If you didn't neglect the viscous effect, what you should do is that you add just viscosity here. Okay? But for the simple case, it says that do not consider the viscosity. And the first step is that, how many variables are there? N is 1, 2, 3, 4, 5. We have 5 variables. And the second step is that the dimensions of each variable. So that V dot as a dimension of, so I will ask this question for you. What is the dimension of V dot? You can write as a comment. So the dimension of the diameter is L. Dimension of the volume is that mass by L to the power of 3. And dimension of the velocity is L by time. And dimension of omega, which is rotational speed, is 1 by second. And these are the dimensions. And then what is the dimension of the V dot? So you can write it as a comment so that I can see what is your joule. Joule is not dimension, joule is a unit. And the V dot, even it is not joule, it is watt. You can see the, if it is work, it will be joule. Okay. If it is work dot, it will be watt. But you need the dimension, not the unit. Okay. What the dimension? Watt by second. There is no unit as watt by second. So you have to write the dimension. What is the dimension of the V dot? The dimension means that you have to write in 7 primary dimensions, like the length, the mass, time. No, that's not. Okay, let me write it for you. So that V dot, it is power. What is power? Power is energy by time. So energy is force into distance divided by time. That's the definition of the power. Okay. And so you can write it as force, you can write it as that mass into acceleration. This is the definition of the force. And then instead of the time, the distance, you can write the d. And instead of the, so everything is okay. And the mass is m, dimension. Acceleration is length, time to the power of -2. And then the distance is L, and divided by time is t. Therefore, you will have m L squared t to the power of -3. This is the unit, sorry, the dimension of the watt. Let me write it here. M L squared t to the power of -3. Okay, so if you have questions till this part, you can ask. Good. So then, now we have found all of the dimensions, which is the second step. Okay. And the third step is that, let me use different color for this one. The third step is that you have to write the primary dimensions. Okay. So that primary dimension. Okay, what are the primary dimensions? You can write as a comment. How many primary dimensions do we have? How many primary dimensions? 3, yes, you have 3 primary dimensions, which is the mass, which is the length, and which is the time. Okay, so mass, length, and time. These are the primary dimensions. Okay, and the fourth step is that, next step. For this next step, what you will do is that you have to select the repeating variables. So if you remember from the past lecture, that the repeating variables are the variables that will appear in each of your in each dimensionless variables. Okay, so repeating variables. Okay. these variables, they will appear in all pi's. So they will appear in all pi's. Okay, the pi's that you generate, for example, pi 1, pi 2, pi 3, in all of the pi's, you will have these repeating variables. That's all. And then let's find these repeating variables. Okay. So if you remember the guidelines, the rules, you cannot select the independent, so dependent variable. So you cannot select work dot. So you cannot select it because dependent variable. Okay. It depends. So it depends on the diameter, density, velocity, and omega. Therefore, it is dependent variable. And for the rest of the values, you have to select omega, v, rho, and the d. From these 4 values, you have to select. So firstly, diameter, you can select it, it's okay. Rho, you can select it. And the v value, you can select it, no problem. And omega, you can select it, no problem. So therefore, for all of these values, there is no any problem. Okay, you can select any 3 of them. Any 3 of them is okay. No problem. You will get the same answers at the result. But first thing here is that if you remember from the previous lecture, we have to, if we are okay, we have to select one geometric variable, one that is kinematic variable, and one dynamic variable. Okay, this dynamic and the geometric variable, and the one kinematic variable. Okay, one geometric variable here is the diameter, purely geometric. Okay, one kinematic variable is the density, which is m to the power of 3. So sorry, this one is dynamic variable because it is mass unit. Okay, so one dynamic variable is mass. It should consist of mass. Okay, this one is the rho. Geometric means that it is consists of L. This one consists of mass, which is the density here, you can see. And the kinematic variable, it consists of the time. Okay. Now you can select the velocity or omega. I've said it. Both are okay. You have to select one of them. Okay. But for the wind turbines, wind turbine, I will select the omega, okay, because the omega is, I think, more appropriate for the power generated by the wind turbine than the velocity of the wind. Okay. That's my idea, but you can select the velocity. Nothing will change. You will get the same answer of the problem. Okay, so therefore, I select the kinematic variable as the omega. Okay. So I have done all of the variables here. So I've selected all of it. Now let's go back to the next step, which is the step 5. Okay, and the step 5 is that generate pi's. 5th step. Okay, you generate pi's. Okay, so firstly pi 1. Okay. For pi 1, what you will do is that you firstly write the repeating variables, which is omega, d, and the rho. So omega and the diameter and the rho to some power. So this one will be a1, this one will be b1, and this one will be c1. And for the next variable, we add the variables that are not repeated. In our case, it is work dot, it is not repeated, and velocity, it is not repeated. Okay, so therefore I add the work dot here. Okay, next time I will add the velocity. So these groups should be dimensionless. M to the power of 0, L to the power of 0, and time to the power of 0. The work dot has a power of mass, L to the power of 2, and time to the power of -3. This one has a power of omega is, so sorry, this one is not 1 by second, this one is 1 by time. So this one is 1 by time. And therefore, okay. Now for the second one, you will have time to the power of -1 and put to the power of a1. For the third one, you will have length to the power of b1. And for this one, you will have the mass divided by volume, which is length to the power of 3. And then you will have the c1. So all of these values, you will get the 0 and the 0 and 0. It should be dimensionless. Okay. dimensionless. And for the mass, first solve for mass. You have the 1 here in the first term, and the 1 here with C1. So 1 plus C1 is 0. And for the length here, you have the 2 value here, you have B1 here, so 2 plus B1, and minus 3C1. It will be 0. And for the time value, you have the negative 3 here, you have the negative A1 here, so negative 3 minus negative A1 should be equal to 0. These are the equations, linear equations, so you can easily solve them. So for the first one, if you solve it, C1 is negative 1. So if you replace C1 as negative 1 here, it will be 3, and the B1 will come to be negative 5. Okay. And from here, A1 is negative 3. So we have the first pi 1. First pi 1 is that work dot, so that A is negative 1, so therefore divided by omega. Okay. B is negative 5, therefore diameter to the power of 5. And the rho is to the power of negative 3. So sorry, an error. So omega is A1, and A1 is to the power of negative 3, therefore 3. And the rho is C1 with the power of negative 1, therefore you will have the rho. This is the first non-dimensionless variable. Okay. This is the first non-dimensionless variable. And then comes the pi 2. Let's solve the pi 2 value here. So that pi 2, instead of omega v dot here, you will write the remaining variable, which is the velocity v. So you will have the velocity omega to the power of a2, diameter to the power of b2, and the rho to the power of c2. That will be the second value. And we'll just write the units, which is L by t. And now omega will be diameter to the time to the power of negative 1, which is a2, diameter length, which is b2, and the density will be mass, length to the power of 3, and c2. Okay, this is the equation. And now, again, let's solve the linear differential equation here, the mass, and you will have the length, and you will have the time. For the mass values, you have the only mass value is here. This should be equal to m0, a0, t0. Therefore, 1 multiplied with c2 is 0. For the length value, you will have the 1 here, plus b2 here, minus 3c2 here. It should be 0. And since c2 value is 0, b2 is negative 1. Okay. And the time value is negative a2. Okay. And there is no any time variable, which is 0. No, there is time variable here with negative 1. So that you have the negative 1 here and negative a2 here. 0. And from here, it follows that a2 is negative 1. And then if you write the pi 2, it will be that velocity divided by a2 is negative 1, so therefore omega. b2 is negative 1, therefore d. v2 is rho is with c2, and it is 0. v by omega d. Okay. So I will ask this question for you. b1 is negative 7, you mean? No, c1 is negative 1, c1 is negative 1. If you replace it here, negative 1 makes 3 plus 2 and 5, b1 is negative 5. Okay. So this is the pi 2. So you can write as a comment which famous formula. You have seen this formula lots of times. This pi 2 is similar. Which famous formula that in physics pi 2 is similar? So v by omega d. That is a physics formula I think you have seen in your life multiple times. There is a famous formula that pi 2 is very, very similar. What is that formula? Okay, which formula do you know? This one is very similar to. Okay, so we'll say it v by Which formula? Okay, let's see. We will have the R by D. No, it includes velocity omega and the D. It includes velocity omega and the D, but it is a very famous formula in circular motion. What's that formula? In circular motion, you have the tangential speed What's that formula? V is omega r. Yes, exactly. You can see this one is very similar to V is omega r. So why it is not exactly the same? Because pi 2 here is, this one is dimensionless. Okay. And dimensionless means that this one is just a number, constant. Okay. So instead of that one, I can write that V is equal to pi 2 into omega d. Okay. So that by experiment, okay, you can find that pi 2 is half, and defined will be omega. And by experiment, you can find that pi 2 is half. You can do an experiment, just one experiment. You can find the relation between V and omega t. You will see that this one comes half. And that is all. And you can see the power of the dimensional analysis. Now, what we have got from this dimensional analysis, the first thing you have got is that the number of variables have decreased. In the previous case, how many variables did we have here? 1 and 5 variables. But after Buckingham's pi theorem, you have 2 variables, which is this one and the second one. Okay. These 2 variables. These 2 variables carry all of the information that these 5 variables carry. Okay. All of the information, all of the relationship that these 5 variables shows is shown by these 2 variables, which is the work done by omega 3, diameter 5, and the rho, and the V by omega t. So in other words, what I mean is that if you plot, for example, that work dot divided by rho omega to the power of 3 and diameter to the power of 5, it was the same. And on the axis, right axis, you can select the V by omega t. Okay. And this relationship between this one, if you do experiment, this is just an example. Okay. You can do the experiment and find the relationship. Okay. These 2 variables is exactly the same as what you can do is that you can find work dot and rho relationship. So for example, you can do that omega d and velocity are constants. Okay, this you can keep these values constant. For example, you get this relationship for constant 1, this relationship for constant 2, this one for constant 3. Okay, you can see, or you can do one more experiment here. We have talked about this one in the tutorial, the theoretical session, and you can do, for example, V dot for omega, and you can keep that omega d and then rho as constant. Okay, so you can get this one for constant 1, this one for constant 2, this one for constant 3. So you can see that a lot of experiments, okay, lots of experiments, but we done with one experiment, okay, one set of experiment, you'll get the same information from all of these experiments. That is the power of the dimensional analysis. This is the first thing, okay? And the second thing is that with this power of the dimensional analysis, now we will find the model as well as the real values. Now let's solve the B part. Not the B part. Okay, so you have the model, okay, similar to the prototype. Okay. If you remember what we are saying as similar, similar means that they are geometric similar, length ratios are the similar, they are the kinematically similar, velocity ratios, they are the dynamically similar, force ratios. This was from the theoretical session. Now if they are similar, so if they are similar, that the pi 1 prototype, is it pi 1? Now let me first finish pi 1 part. And we have found that work dot is function of rho omega, this one given v, and we have shown that this one work dot divides by rho to the power omega to the power of 3 and diameter to the power of 5. It will be function of, now different function of v by omega d. Okay. This one was the second, so this one was the first variable set, and after that pi theorem we have found this one. Okay. In other words, you can say that or pi 2, this one is the pi 2 or pi 1. This one is pi 1 is function of pi 2. This one what you have got. In this first case, it was given in this manner, but after pi theorem, you have found that the pi 1 is function of pi 2. Okay. This is the same stuff, but I'm writing it as pi. What the pi means is that the scientist who has invented it called it as pi, because pi is also dimensionless. But this one doesn't have any dimension. Therefore, the name as pi is called as pi. Okay. And then, since we have this information, and since they are similar, if they are similar, now what it says that, so independent pi's should match. Independent pi's should match. What it means, pi 2 for the prototype should be same as pi 2 for model. This one is dependent. Okay. So independent pi's should match. If independent pi's match, if this one happens, and then pi 1 model will be same as pi 1 prototype. Dependent ones. These are dependent. Because it's a function of that one. If pi 2 is match, then pi 1 is also match. Okay, that is the issue. For our case, it is a similar. It says that the model and the prototype are the similar, and therefore all pi's match. Okay. So if similar. Okay. Therefore, if it is similar, all pi's should match. Okay. Now let's do that part. And since all pi's match, so we can write that work dot rho omega 3 diameter to the power of 5 for the model should be same as work dot divided by rho omega 3 diameter to the power of 5 by prototype. These two should match, okay, because we have said it, if the independent pi's match, for similarity it should match, and then the dependent also matches because it's a function of independent pi. It's a function of that one. Okay. Therefore, all pi's match. So we will say that this one is equal to that one. Now let's write the values that are given in the question for the values here. The question says that work dot for the model is 280 watts. And let me write it here. Model is 280 watts. Okay. And for prototype, it is unknown. Density in the question, it says that it is same for both. You can take 1.2. Density is the same. And omega for the model is, let's go back to omega value. For the model is 1200 RPM for model, but for prototype, it is also unknown. Okay, let me write it. 1200 RPMs here. But you should convert it into SI units. You have to work with SI units, but for this problem, it doesn't matter because they are at the downstairs, they cancel out, but for generality, you have to work with SI units. Therefore, it will be 1200 multiplied with 1 revolution is 2 pi. Okay? And 1 minute is 60 seconds. Or you will get the value here for SI unit. Diameter for the prototype is 90 centimeters. It's 0.9. And diameter for the real one is, prototype one is, if you remember, 50 meters. It was 50 meters. And the only unknown for the part here, so there are two unknowns actually, omega and the v dot. This is the first equation that doesn't help us. And the second equation should be that next pi's should match. The velocity divided by that omega d, this one for the model should be same as velocity by omega 50 for the prototype. Okay. And for the velocity of the model, let's write it. Velocity for model is u infinity. This is the velocity of the wind, which is 12 meters per second. This one is 12 meters per second. And for the prototype, the velocity is given as 8 meters per second. Okay. 8 meters per second. And then for the omega value for the model, it is given as 1200 RPMs. I will write in SI units 1200 multiplied with 2 pi and divide by 60. For the diameter, it is the value of the diameter for the model is 0.9. For the prototype, diameter is 50 meters. And here only unknown is omega. So from this equation, you can get the omega value of the prototype. And replace back here, and you will get the work done. So let's first solve this part. What is the omega p for the prototype? And then we can go back to the second one. So if you have the values for the omega, you can tell me. I will write it. Okay, what is the omega value for the prototype? You can just calculate it. And with this one, we will finish the example and move on to the next example. Let me help you a little bit. So you have the 50, 12, and then divide by 8. No, it should be opposite actually. Eight multiplied with 1200 multiplied with the 2 pi and divide by 60 and multiplied with 0.9. So this one was for this part, and then you should divide into 50 meters diameter and then 12 meters per second. From here you will get the omega p. Similarly for here, let me write it in. So that worked out for the prototype. It should be got 280 multiplied with 1.2 and multiplied with the 50 to the power of 5. Okay, diameter. Omega prototype, so I will write it here to the power of 3. And this one worked out prototype. Okay, this one is the prototype. I've written all of the values, yes, and it should divide by 1.2 here and multiplied with 1200 with the 2 pi by 60, and it should be to the power of 3, and then you have to multiply it with the 0.9 to the power of 5. Okay. So does any of you have the, so omega p is 1.5. So what is the unit? Is it the radians per second? We have said it, the units are radians per second. The 1.5, we have said it, radians per second. Okay. You can actually convert it into back to the revolutions per minute. What you can do is that it is 1.5 multiplied with the 1 radian. So it will be, you should divide by the 2 pi, because 1 radian is 1 by 2 pi, and the 1 second is 1 by 60. It should be multiplied with 60. And from here you can get the value for the omega, which is in RPM unit. Okay, let me erase this one. Equal, and this one will give you the RPMs. And then if you replace that 1.5 to the power of, that is 3. and you can get the work done of the prototype. So I don't have enough time, therefore I stop it here, but you can calculate by yourself. Let me see. This one, I think it should be 14.4 revolutions per minute. Okay, but this one should be, you can calculate it by yourself. Okay, I don't think that I have the value for this one. You just replace the values here and get the value of the power here. Okay, you can calculate it. All of the values are here and just replace it. Okay, we have finished the first question. You can see that by dimensional analysis, you can, that this one is the real one. It is a large one. You can do a model one and find the values and extrapolate those values to the real one. Okay. So now comes the next question. You have an axial flow pump for cooling system of a nuclear reactor is required with the following specifications. Okay. You have the head of the pump, you have flow rate of the pump, speed, diameter, water density, and the power. Okay. The manufacturer of the pump builds a model, but due to available test conditions, they can use electrical power up to 250 kilowatts and the flow of 0.25 meter cubes per second. So this one is all of the values here. For example, head of the pump, it is prototype, flow rate is prototype, speed is prototype, diameter again prototype, water density again prototype, and this one is prototype. And this one is the model, and this one is the model. They have built a model one to understand what happens in reality. And the efficiency of the model and the prototype are the same. They have the same efficiency. Eta, same. Answer the following questions. And using Buckingham's pi theorem, generate non-dimensional parameters using GH and the BHP is a function of V dot, D, epsilon, omega, rho, and the mu. This is the first step. Find the head impeller rotational speed, and the impeller means that it is the blades of the pump, because inside the pump you have the blades that are rotating, and those blades add energy to the fluid. Okay. And the impeller rotational speed and the scale ratio, okay, ratio of the model. And then this one means diameter. For example, diameter prototype divided by diameter model. And calculate the dimensionless specific speed. So this one you can ignore for the time now. You don't need to do it. So you can ignore this part. Okay. You can do only A and the B parts. Okay, with the dimensional analysis. So it says that whenever you see the model and the prototype, it means that you should use the Buckingham's pi theorem. Okay. So I will write the given values here. The first step is that the GH is G is gravitational acceleration 9.81 meter per second squared, and the H is meters. Okay. And the BHP is power. It is, that means brake and the horse power. Okay. That is BHP, because if you have a pump, that pump uses some electric power. That electric power, power supplied by the motor, because you have the pump here, okay, and that pump is connected to a motor with some the shaft. Okay, this one is the shaft, and this one is motor, and this one is the pump. This motor applies some shaft torque on the pump, and therefore here you have the impellers. The impellers rotate. Okay, these are rotating, and the power that is supplied by the motor to the pump, it is called BHP, or brake horsepower. Brake horsepower. These are old name, but used anyway. So now let's solve it. So GH, it is given in the question that it is function of V dot, diameter, epsilon, which is the wall roughness. If epsilon is the roughness of the wall. If you have the wall of the, for example, pipe, this is the wall of the pipe. But when you look at it, it looks very smooth. When you take one section of it and zoom in, and you will see that it is not smooth, but it has some roughness elements. And you can take the average roughness height, and that will be the epsilon here. The average roughness height, epsilon. Okay. So that omega and the rho and the mu, which is the viscosity, Now let's write this one as a function of, it will be v dot, it will be a function of the diameter, it will be a function of epsilon and the omega and the rho and the mu. Okay. This one for the GH, it says that BHP also. The BHP is also the same function of it, but so same variables but different function. V dot and diameter, epsilon, omega, rho, and the mu. Okay. Now let's select the. So first for this one, so I will not do all of the steps, but I will just do some of it, but you can do the rest by yourself. Okay. So that n number of variables is 1, 2, 3, and you have 3 more and the 1 there, 7. You have 7 variables, and the primary dimensions, j, I will write that one, 2. But firstly, let's write the, so this one, for this one, GH, so I will let you for this one, what is the dimension of this one, and for V dot, for the second one, the dimension is that volume divided by time. So L3 to the times -1, and the diameter is L, epsilon is L, and the omega is epsilon. This one is length, omega is 1 by time, and the rho is length, so sorry, mass, length to the power of -3. And then you have the viscosity. And viscosity has a unit of kilograms per meter second. And therefore you will have the mass, that meter -1 and time -1. Okay. This one is viscosity, this one is that rho and the omega and the epsilon and diameter V dot. What about the GH? We would say the dimension of the GH. And if you write these dimensions, and you will see that the J is 3. So you have the length and time and the mass. Okay. Therefore, you have the 3 repeating variables. Okay. And now let's select the repeating variables. Firstly, you cannot select the GH. You cannot select it because it is dependent variable. Okay. Cannot select it. You can see it. You cannot do that. And then you cannot select the epsilon and then the viscosity. You cannot select epsilon and the viscosity, okay, because they are not common. Okay. They are not common. Okay. Common means that everybody has an idea about it. Okay. Epsilon and the mu, it is not so common values, common variables. Therefore, we don't select it. And my method says L time to the power of +2. You should have, let me write it. So the G has a power as a unit of acceleration. Acceleration has L time to the -1, 2. And the H has a unit of height. This one is meter. Okay, GH. H. So you can think of this one as mgh divided by m. M cancels out, you have the GH. So that H will be L, and therefore you will have the L squared time to the -2. Okay. So I've said it, GH is a dependent variable, you cannot select it. Epsilon and the mu, you cannot select it. Okay. What is left is that V dot, D, omega, and the rho. And the V dot is more complex. You cannot select it, it has that more complex dimensions. Okay, so that with respect to omega, it has more complex dimensions with respect to omega. You can see that omega carries the similar information that V dot carries. Okay, therefore, V dot omega is better. So therefore, I will select the omega, which is the kinematic variable, and I select the D, which is geometric variable, and I select the rho omega D, and this one is the dynamic variable. Okay. So the repeating variables will be that rho, omega, and D. You will do the similar, exactly the same steps as for the next one, which is the BHP. Let's first finish this one. And if you do the previous steps that I have done, you will get the non-dimensionless variables So for pi 1, it will be that GH multiplied with that diameter to the power of A1, and then omega to the power of B1, and then rho to the power of C1. And this one will be equal to m to the power of 0, L to the power of 0, and time to the power of 0. Okay. You can just write it and solve it. This is for pi 1, and the pi 2, you will have the GH and the diameter to the power of, so I have done the GH part. I will need to the next value. This one will be the pi 2. For pi 2, you will have the V dot, the remaining variables. V dot, diameter to the power of A2, and omega to the power of B2, and the rho to the power of C2. For pi 3, you will have the epsilon, and diameter to the power of A3, omega to the power of B3, and the rho to the power of C3. This is for pi 4, pi 3, and the pi 4, you will have the viscosity. It will be that diameter to the power of A4, and omega to the power of B4, and rho to the power of C4. And you will solve, all of them should be m to the power of 0, L to the power of 0. All of them should be dimensionless. Okay. All of the values here should be dimensionless. If you solve these equations as the similar steps as the previous one, which is the Buckingham's pi theorem, and then you will get, so I will write just the final answer. For the first one, you will have the GH divided by omega squared and the diameter squared, which will be pi 1. Okay. And the pi 2, you will have the V dot by omega d to the power of 3. This one will be pi 2. And the pi 3 will be at epsilon by d. And the pi 4, you will have at mu divided by rho omega diameter squared. Okay. This is for the first set. These are the 4 first part of the question. And the second part says that now the similar steps for BHP. Now I will do the similar steps as for BHP, and I will write that BHP is again functional, but different function now. It's function of that V dot d epsilon omega. And then you have rho and mu. Okay. And similarly, you will choose the same non-dimensional variable, okay, because only here dependent variable change. You cannot select the BHP because it is dependent variable, and from these options you will have the 3 of them. Again, n will be that same number, which is 7, and j will be 3, and for this j you will select the rho omega t. And now you will have the pi, say that pi 5 will be BHP, and multiplied with that d to the power of a5, rho to the power, so omega, let me be in correct order, rho omega to the power of b5, and rho to the power of c5. This one should be equal to m0, l0, and the t0. Similarly, pi 6, you will have the, instead of BHP, and so the power of the unit of BHP, I have not said it, unit of BHP is watt. Okay. This one has a unit of watt, and for the BHP, let me add it here. BHP has a unit of watt, and for the previous question, so we have found the work dot. You know, it has a unit of the watt. So we have solved it for watt unit here, and if you remember, mass into acceleration in diameter divided by time, and we have got that it should be mass length to the power of 2 and the time to the power of -3. We'll have the same one. Mass length to the power of 2 and time to the power of -3. The same, because bit is BHP and it has the same unit as watt. So V dot. Okay. So with this one, now comes the second, one more that pi's are there. So you will have the pi 6, it will be V dot divided by diameter to the power of A6, omega to the power of B6, and the rho to the power of C6. But you can see that pi 6 is same as pi 2. You can see these are the same. A2, B2, C2, it doesn't matter, and they are the same. It will be equal to pi 2. And similarly, pi 7, and you will have that for epsilon and diameter to the power of A7, omega to the power of B7, and rho to the power of C7. Okay. And the pi 7, you can see it is same as pi 3. They are the same, and the pi 8, it will be equal to now mu and diameter to the power of A8, and omega B8, and the rho to the power of C8. And this one will be the same as pi 4. Okay. If you solve these equations, linear equations, and the final answer will come to be, so pi 1 will be BHP by rho omega to the power of 3 and diameter to the power of 5, and the pi 2, pi 3, and the pi 4 are the same. They are the same. So we have done the first part of the question. It says that using pi theorem, we have generated all of the non-dimensionless variables. And the B part of the question says that find impeller rotational speed, head, and the scale ratio of the model dm by dp. So this one dp, by using the variables given in the question. Okay, so there are some variables. For example, the flow rate is given, so you can convert it into meter cubes per 3600. It will be meter cubes per second. And this one, you can convert it into SI unit. You will multiply with 2 pi and divide by 60. And this one is that 1.2 meters. And this one is the density of the prototype. And this one is the power of the prototype, which is 2000 kilowatts, or you will have that 2 million watts. And this one is for the model, and this one is for the model 2. Okay. By using the values that are given with the same as the first question, you have to find the model values. Let me write that part too, and then I can finish the question. So that all pi's should match. All pi's should match. Okay. This is the question. Okay. All pi's should match. So first pi I'll select is that GH divided by omega squared and the diameter squared. This one for the prototype should be same as GH by omega squared and the D squared for the model. This is the first one. Okay. And the second one, you have the V dot, so by omega to the power of, so you will have the second pi, which is V dot by omega diameter to the power of 3 for prototype, should be same as V dot omega diameter to the power of 3 for model. And the third one, you will have that BHP for that rho into, so BHP divided by rho omega to the power of 3 and diameter to the power of 5 for prototype should be equal to BHP for rho omega diameter to the power of 5 for the model. But for the pumps, so this you will see in turbomachinery class, so that pi 3 and this one and that one doesn't play any role in similarities, okay? Because these two numbers are always matching, okay? It doesn't play any, so that the length ratios for the pi 3 and the pi 4, it is not so important for the model and that for the prototype, okay? Because they are always similar, okay? No problem with these ratios here, not consider it. But even you are interested, you can write it. But then it will not give you any new information. Okay, so if you do that, you can write the values that are given in the question. And the question says that the G is same for both of it. And for prototype, it is 85 meters. Omega, if you write it, it is 156, and diameter is 1.2. Okay. For prototype, that omega is unknown, this one is unknown, and the H is unknown. Model, sorry. For prototype, again, this one is 2.78 meter cubes per second, and the omega is 156 radians per second, and diameter is 1.2. And for prototype, you have that 0.25 meter cubes per second, and this one is unknown, and that one is unknown, okay? And the BHP for the prototype, it is 2 times 10 to the power of 6 watts, and the rho is 714, that is the rho value. And then you have the omega value, which is at 156, and diameter value is 1.2. The BHP for the model is 250 times 10 to the power of 3, and the rho value is 1000, and omega value is unknown, and diameter value is unknown. By using these equations, by using these 3 equations, and you can find the values of the D and the omega as well as H. So you will get D for the model, it will be 0.3608 meters for the model, and the omega for the model is 516.9 radians per second. And then for the H, it will be 84.29 meters. You can solve the equation and get the values here. Okay, but you should know that, as I said, that epsilon by D, and the next one is mu by rho omega d squared. Mu by rho omega d squared. Okay, not so important. Okay, in pumps. It can be in pumps or turbines. Okay, they are not so important because you will see that this one is a Reynolds number. Reynolds number is high for each of it. Okay, and therefore due to that high value of the Reynolds number, the epsilon by D plays the same role as in the pump model or as in the prototype model. Epsilon by D plays the same role. Therefore, it is not important to worry about the epsilon by D and also this Reynolds number, because at high Reynolds number, the flow pattern becomes the same, almost the same, and therefore that again there is no. So if the Reynolds number were very different, for example, if this value was too high for the model, too low for the prototype, yes, then we could carry about it. But since it is very high for both of it, and epsilon by D, due to that higher value of the Reynolds number, plays the same role, and therefore no need to worry about these 2 values here. Okay, so with this one, I finished the example 2, and I stopped the recording. But if you have questions,